Hello, my name is Alexander Gall, and I'm happy to present our paper ImNDT, an immersive workspace for the analysis of multidimensional material data from non-destructive testing. Let's start with a motivation. Composites like fiber-reinforced polymers are used in safety-critical application areas like automotive, aeronautics, medicine, but also leisure industry. And this is due to their properties of having a very high strength-to-weight ratio and an increased stiffness. Therefore, inspections are essential to ensure the increasing demands on these materials. To inspect these materials, we now can use techniques from non-destructive testing, like X-ray computed tomography, which provide us with 2D images. These 2D images can then be reconstructed to create a 3D volume. This 3D volume is now our primary dataset, which has voxels with different intensities. In the case of fiber-reinforced polymers, the material consists out of fibers, and these can be segmented and classified, which gives us a multidimensional dataset, the so-called secondary dataset. And this consists out of the start and end point of these fibers, their length, their diameter, or their orientation. Here we can see some examples of how the experts are currently analyzing the material data. Let's take a closer look at, for example, the OpenIA tool. And as you can see, the current workflow is primarily designed for numerical evaluations through statistical values and 2D charts. So we can see also some 2D views of the data, but despite working here with inherent spatial data, the actual 3D volume is usually displayed only in a small view and just for orientation. And this can also be seen for the other examples here. So the current approaches focus heavily on these two-dimensional graphs representing these numerical values and additional some 2D views of the data. But less focus is directed at extending the spatial representation with abstract information in this immersive environment. So this 3D representation is not in focus in these applications. Our tool, ImNDT, now takes advantage of this enhanced spatial perception in VR to investigate the complex structures of these materials. We use immersive techniques to enable a fluid and natural exploration with embodied navigation and the avoidance of menus and manual mode switching. Let's start with the immersive workspace. So as you can see in the center of our environment, we have the fiber model, and the model is subdivided by an octave structure, which you can see from the violet boundary around it. We render the fibers as cylinders through a model-based surface representation to make it easier to work with them. With this spatial structure and focus, the exploration can start. So we look at our first visualization interaction tool called the model in miniature. So as you can see here in this image, in the center of the environment is still the fiber model, but over the user's controller, there hovers this miniature model, which follows the user. And this is an abstract representation of the fiber model. So it acts as an overview and an intuitive navigation tool and mimics the octave division of the fiber model and is able to display additional information about the region. So you can see here we have a color legend. The model in miniature shows through a 3D heat map the distributions of the fiber's characteristics in the different regions. And in the back, behind the volume, you can see the maximum intensity projection, which shows, based on the user's current viewing direction, the highest value through the rows and colors of the fiber model. And here we have a video of it. So you can see here that the user changes the subdivision of the fiber model to get small and more detailed regions to have here a more detailed analysis of these areas. And behind the volume in the viewing direction of the user is always this maximum intensity projection, which shows the highest value for this row or column. Next, we want to look at in the interior of this material. So we have an exploded view for this. And we have different forms of displacement for these regions. So the first one is a so-called structure-disturbing displacement. And here, all regions are shifted by their interval distances from the center outwards. So the user retains the structure of the material and still has the possibility to look inside. Then we have a so-called radial displacement, where the structure of the fiber model changes slightly, but this offers the possibility to have these radial outward shifted regions where you can step inside and look at the material from the inside. And lastly, we have this octant displacement, where the regions are shifted in the 8 octant directions. And so we still preserve some of the structure of the material and have a really good look inside and see the inner sides of these regions. Next, we also have a similarity network. And the similarity network now abstracts the fiber model through cubes and links. And the size and color of the cubes identify how many fibers are in this region. So it shows the density at this point in the material. And the links between these regions show the similarity between these regions. So we can see how many fibers these regions have in common. And so the expert can see through this representation where dense areas are and in which prominent direction these fibers traverse through this volume. Next, we have the histobook. So the expert also wants to see the distribution of these characteristics in more detail between these regions. And so the user has the possibility to select up to two regions for which you can then compare the distribution of the fiber characteristics in more detail. And these histograms are organized using a book metaphor. So through a page turning gesture, the users can switch between these different distribution and look them in more detail and see the difference between these regions and what they're made out of. We also tested our tool with domain experts through a qualitative user study. We had 11 participants, and the procedure was around 15 minutes of introduction to the tool. And then we had 25 minutes of an exploration task with a think aloud approach. So the expert could really try their typical material analysis in our tool. And afterwards, we have 25 minutes of a semi-structured interview to really get these valuable feedback on the strengths and weaknesses of our immersive exploration. And lastly, we have a Likert scale with around 12 questions where the expert could then rate the developed techniques so we get more detailed information which techniques work best in this immersive setup. And the overall feedback of the experts were very positive. So we got some comments like, you can fully immerse yourself in this data and that you can have a very good feeling for the specimen. So they also mentioned that it would be for them of interest to really use our tool in their current analysis process. And they also noted that ImNDT is particularly interesting for students and customers who need an intuitive and a nice representation of the structure so that they really know how these materials are formed. So to conclude, ImNDT provides a novel immersive exploration of secondary NDT data, a visual metaphor and interaction techniques like the model in miniature, the exploded view, similarity networks, Histobook for the analysis of such composites. And lastly, we had a qualitative case study with domain expert to really identify the usability of the framework for material science. And with this, I want to say thank you for your attention, and I'm happy to answer questions.